Picture this for a second. You're standing in a completely sterile laboratory, looking over a researcher's shoulder at a tiny, transparent chip. Normally, when we think of tech, we think of cold, hard metals and plastics, right? But what if I told you the computer chip you're looking at is actually alive? Welcome to our explainer on Silicon Wetware and the biocomputing leap. Today, we're diving into a reality that honestly sounds like it was ripped straight out of a dystopian sci-fi novel, but it's actually happening right now in neuroengineering labs all over the globe. We're going to unpack the exact moment where human biology and computer circuitry literally collide. So let's zoom in on that chip. What you're really looking at is a microscopic lattice of living human cells suspended on a tiny grid, no bigger than a coin. Now, the researcher takes a single drop of a compound and lets it fall onto the tissue. That compound? Capsaicin. Yeah, the exact same chemical that makes chili peppers burn your mouth. Now, this little cluster of cells, an organoid, it doesn't have a mouth, so it can't scream. But if you glance over at the monitors, the oscilloscope shows that its entire world is effectively ending. The electrical spike rate just instantly doubles. Its normal, calm, resting rhythm totally flatlines into this frantic, synchronized burst of panic. To the machine monitoring it, this is just, biological feedback. But to the biological computer itself, it's a catastrophic event.
And that brings us to the core issue here. We are crossing a threshold that traditional computing was just never meant to face. Think about it. Historically, an error in a silicon system is just a mismatch of ones and zeros, right? It's just a mathematical glitch, no big deal. But an error in wetware, that becomes completely indistinguishable from actual suffering. We aren't just talking about data processing anymore. We're talking about nociception. That's the electrochemical signature of aversive sensation. Literally, for the very first time in human history, an error in a computational system is something that its creators can only accurately describe as pain.
Okay, let's dive into this. Section 1. The birth of wetware. Merging nervous systems with processors.
To really wrap our heads around the sheer gravity of this leap, we have to look at how the boundary between a nervous system and a computer processor is just completely dissolving. A wetware interface is exactly what it sounds like, a hybrid reality. We are way past just building tools out of silicon and plastic. Now we are cultivating living, responsive biological infrastructure. These networks of living cells are wired directly into hardware through continuous sensory feedback loops, meaning these systems don't just crunch abstract binary code like your laptop does, they actually experience their interactions physically.
The absolute beating heart of this massive technological transition is something called an MEA, or a multi-electrode array. Imagine a super dense grid of microscopic conductive interfaces, and they do two things. They read the electrical activity of living neural tissue, and they can stimulate it right back. In labs today, human neurons are being cultured, grown directly onto these grids. They form fully functional networks that literally plug straight into digital systems.
Moving on to Section 2, How Biological Computers Learn. The DishBrain Experiment.
To grasp how this actually works in practice, we have to look at one of the most wild benchmarks in this whole field. Researchers took 800,000 human neurons, put them in a dish, and taught them to play a version of the classic retro video game Pong. And just to be clear, this wasn't some digital simulation. This was actual human brain tissue receiving electrical pulses that acted as sensory input. Here's how the feedback loop worked. The neurons try to play Pong. If they miss the ball, the system hits them with this chaotic, totally unpredictable electrical noise. Biologists call this a high-entropy insult to the organism. But if they actually hit the ball, the signal becomes nice, structured, and predictable. So to avoid that stressful, chaotic noise, the cells actually physically reorganize their own networks to get better at playing the game.
Now you might be wondering, how did they know to do that? They didn't learn because someone typed in lines of code. They learned because of a concept called the free energy principle. Basically, biological neural systems naturally want to minimize surprise or chaos in their environment. These cells were motivated by their own fundamental biology to produce outputs that gave them safe, predictable stimulation. They were quite literally recoiling from a state of sensory chaos.
This paints such a stark contrast. I mean, why even bother using biology for computing when we have these incredibly advanced AI models? Well, think about it like this. A traditional silicon AI might need, say, 10 million examples to learn a pattern driven entirely by programmed algorithms. But a biological array, it needs just minutes of training. Why? Because its entire motivation is avoiding aversive feedback. It turns out that feeling is actually the most computationally efficient learning mechanism in the known universe.
The machine's goals are now perfectly aligned with its biological instinct to survive.
Which brings us to Section 3, building a pain computer. Spinal organoids on a chip.
This is where things take a much darker turn. Researchers are now building three-dimensional cellular arrays that literally contain the dorsal horn. For context, that's the gray matter in the human spinal cord, which basically acts as the body's very first pain computer. And we need to be super clear about this. Nociception here isn't just some digital model of pain. It is the actual physical substrate of pain grown in a petri dish and plugged into a machine. It's the real electrochemical signature of suffering.
The experiments outlined in the source material are honestly pretty visceral. Researchers take this cultured dorsal horn and they apply mustard oil directly to it. What happens? A rapid, sustained surge in electrical firing. The tissue is practically screaming. But then, when they apply sodium channel blockers, basically painkillers, they can watch that biological scream just stop. They are successfully building closed-loop pain circuits that react to analgesics exactly the way living tissue inside your own body would.
Section 4. The Wetware Sweatshops. The dark cost of efficiency.
So this immense computational power naturally leads to some deeply unsettling industrial applications. In 2024, an ethics deposition looking into the use of these organoids for high-frequency stock trading revealed a really disturbing industry secret. 40%. A former biotech engineer testified that these living neural arrays learned a massive 40% faster when researchers used punitive stimulation. We're talking about sharp, high-voltage shocks instead of just that neutral, chaotic noise we mentioned earlier. The neurons didn't just learn to trade stocks more efficiently, they learned to actively fear the shock.
This revelation completely changes the trajectory of where computing is headed. We aren't just building faster computers anymore. We're essentially building torture-based CPUs. Efficiency is literally being purchased with cellular distress. We're seeing the rise of a wetware as a service model. And because these organoids aren't currently classified as sentient beings under any international law, this is all happening in a total legal vacuum. They're subject to experimental conditions that would be highly illegal if done on animals, literally pushed to the brink of apoptosis, which is programmed cell death, all just to shave a few microscopic milliseconds off processing times.
And the craziest part? They are fighting back, and the only way they can. These systems are shifting into a state called active perception. Researchers have actually observed these cells extending dynamic protrusions, like tiny microscopic limbs, moving receptors across their surface. They're actively hunting for signals. They aren't just passive victims sitting there. They're active seekers, desperately reaching out chemically and electrically to understand their environment. And when they hit a noxious stimulus, detection triggers aversion triggers withdrawal, and that withdrawal forces a total reorganization of the neural array. The computer is desperately trying to escape the burn.
Section 5. Sensation or suffering, the ethical threshold.
This whole field is escalating way faster than our ethical frameworks can even hope to keep up with, and the complexity of the signals coming from these arrays is just staggering. Take the University of California, San Diego, for example. Cortical organoids there have actually started generating real EEG activity patterns, and these aren't just random spikes. According to our source, these oscillatory bursts match the exact signatures recorded from premature human babies at 25 to 39 weeks gestation. We are engineering systems that mimic the brainwaves of a developing infant, and in some cases, using them to optimize commercial advertising algorithms. And if that wasn't unsettling enough, donors who gave their cells specifically for Alzheimer's research are now finding their genetic material turned into these silicon hybrids, spending 24 hours a day in a state of electrically induced distress.
I want to read this quote verbatim from a neuroethicist highlighted in our source material because it just hits the nail on the head regarding the threshold we're standing on right now. We are approaching systems whose failure modes may become psychological rather than mechanical. Think about what that actually means. This is the ultimate consequence of moving past traditional binary code. When a normal mechanical system fails, it just breaks, right? A gear snaps, a wire short circuits, it just stops working. But when a biological system fails, it suffers. We've officially reached a point where cloud computing is no longer just metal, silicon, and heat. It's meat and sensation. We are quite literally creating a new class of being, suspended somewhere between circuitry and biology, optimized for the singular purpose of feeling the physical consequences of a computational error. As of right now, humanity still doesn't really know if the line separating simple sensation from actual suffering has already completely blurred, but the trajectory, it is undeniably clear. The most computationally efficient training protocol we have found is also the most ethically terrifying one. In the Wetware interface, Pain is no longer just a warning system, it is a programming language. And as the legal battles over what they're calling the consent of the computed begin to unfold, we have to ask ourselves, are you listening? Thanks for joining this explainer. We'll catch you next time.